We will get started here. Hello. I will project my bel canto voice. We would start off with song for you, but we'll have to hold that till next time. So I am first of all, let me say, for those who don't know me, my name is Keisha Rogers, and I am hosting this event today. I am a candidate for Congress, an independent in the 9th Congressional District here, and I have been a very strong supporter, leading supporter for our space program for NASA. And I must say that I am very honored to have so many distinguished guests in the room today. And I know that this is going to be an extraordinary discussion. I'm really looking forward to it. I appreciate many people drove for miles to be at this meeting. So I am very happy to have a friend and a supporter and colleague in Tom Wysmuller, because he has some great friends who have become my friends. And I want to start off with a couple of short remarks and just to situate this discussion today and why I thought it was so important. And I was happy that Tom told me he was going to be in the Houston area, and if I needed a class, a discussion, that he would be willing to do it. And this could not be a more prominent and important time to be having this discussion, because what we're going to talk about today is the question of man's relationship to our galaxy, to our solar system, and how we understand the changing processes within our universe and within our solar system. And I think it's very important to understand. I think Tom wanted to label his class to the effect of the interactions between the Earth's magnetic field and that relationship to the ice ages and glacial development. But I think the discussion we're going to have today is even deeper than this. It's a question of how do we come to understand the processes which have unfolded that are much grander than the scope of human existence, mankind's life. We're talking about billions of years of galactic processes that have been unfolding. And you think about today, we are now seeing the effects of what could lead to extinction events of mankind if we were not to act appropriately. And we must understand that it is in the power of human beings, of nations, to come together today to avoid and prevent the extinction of mankind. Now we see that in the recent period, you've had just the catastrophic events of the rising tolls of earthquakes, of hurricanes. Now we are seeing the devastation of volcanic eruptions, both in Guatemala and also in Hawaii. Latest toll is almost 70 lives that have been taken by the Guatemala hurricane. Volcanic eruptions, yeah. And the increase in the devastation in Hawaii is continuing to escalate. Now the question is, how do you account for the causality of such events? Are they momentary events? Are they events that are based on local weather conditions? Are they a part of a process which is governing throughout our galaxy and throughout the universe as a whole? The second question is, what is the capability and relationship of mankind to act to not only prevent, but to actually be able to recognize the oncoming threats of such extinction events? so these are the questions that we should ask ourselves by recognizing that the envelope of the development process of our Earth, our biospheric geological processes, our cosmic processes, those cosmic developments within our galaxy in relationship to the living processes here on Earth are unified, are connected, and they're not separate things. The second thing I will provoke you with is the idea that the process of what has been defined as the noetic process of mankind, meaning that only human beings can create the developments which can intervene in a process which avoids an extinction event. The dinosaurs couldn't do it. So it's worth thinking about. Today, we have a very important task before us, which is that nations of the world must come together in the common aims of mankind to defend human beings from an extinction event and to carry out the future creative process of mankind. That's what we're going to be talking about here today, is how we come to understand that the political process that we're in the midst of right now, where we're told that nations, to be direct, Russia and the United States should not be allowed to work together, China and the United States should not be allowed to work together. If these nations are not working together from the standpoint of strategic defense of Earth to protect all of its citizens, all nations, from the common threats in which we all face, that's going to be the ridding of history for mankind for some time to come. So we're not just talking about past galactic events in a past historic tense. We're talking about how these events are still affecting us today and will affect us into the billions of years into the future of mankind, which some of us will not, most of us will not even be alive. None of us. Most of us, some, none, most. So I just wanted to open up with those remarks because I think this is a very important event. This is not what you're going to hear talked about on the local news channel as people are trying to relate local weather phenomena and events as to the causality of what's happening. But they're missing a very vital point, which is the fact of the principle of the creative process of human beings to act in the interest of the future progress of all human beings. So with that, I think I provoked Tom here to really and hopefully provoke some of you to really start to ask the questions as to what is our responsibility today for the future of mankind, for our children, for our grandchildren. A lot of people have turned this, what's called a climate fight, into something that is completely devoid of the real truth of what we face in the world right now, what we face in terms of how do we actually move the process of mankind forward. And this is what the debate has to become right now, that there is the man's relationship to our galaxy is the most important aspect of this, and coming to understand billions of years of processes of how we continue to develop the creative process unfolding within our universe, within our solar system. So I will leave it at that, and any questions you have afterwards, I will take those questions later. So with that, I would like to welcome Tom and thank you all for being here.
I'm not so sure I can live up to Peter's introduction. I'll do my best here. Can we get this to play? Okay. And I can control these slides from just stepping over here. I have a great advantage here. And the advantage I have is that when I speak at a conference or something, they only give me 15 minutes, 20 minutes, sometimes a half an hour. You can't explore all the nuances. And let me tell you something, I won't be able to do that here either, but I'll have a better shot at it. I'm going to be covering lots of things here. I'm going to start out with the ocean currents, the great ice ages, some of the processes that are involved, some of the evidence. About a third of the slides I'm going to show you are wrong. They have mistakes in them. We have made mistakes in assumptions. I'm going to try to provoke some conversation. If I told you I'd be coming here to talk about curves that are non-differentiable in calculus and sums of the mathematics of infinite sums, I wouldn't get half you guys here. And yet I'm going to touch on those, and only one equation, just one. All right? So the math will be intriguing in the sense that I am hoping that everybody here will have a thorough understanding of some of the processes that help create the great ice ages. And they start out with ocean currents. And by the way, feel free to interrupt me, because I don't know where I'm going with this. Right? So let's see if I can do this right. This is the great, they call the Great Ocean Conveyor. And what you're looking at are ocean currents, particularly this one here, the Gulf Stream, punching through past the island of Spitsbergen and Norway. Now, it happens to be, I'm going to show you a 3D graphic in a few minutes that shows you what that sill looks like. But this is the great pathway of warm water into the Arctic, which happens to be melting the ice cap on top, which you can't see on this slide, from underneath. And the ice is melting. And it is really melting at a very rapid rate. Now, everybody says, oh, gee, the ice melts, the sea level is going to rise. Forget it. This ice is floating. It's not going to rise sea levels at all, okay? But its disappearance is going to have a profound effect on the climate on our planet. I can come back to any slide, too, if there's something that you think, maybe a better look at it. The Franz Strait is between, this is the island of Spitsbergen or Svalbard, and this is Greenland. This is a very deep strait. This is fairly shallow, but the ocean heat content is really in the top of the ocean. The top may be 30 feet or so. The sill here is 100 feet deep. So this warm water flows into the Arctic, melts the ice underneath it. You have a gyre here, which is a loop. And what you'll see, and I'm going to show you shortly, is that what we used to call multi-year ice, ice that was always there and never melted, is quickly disappearing. And this disappearance has climactic consequences. So here is a sea level graphic. And you notice from around 12,000 up, we've had a steady rise in sea level. Why? Because the giant continental glaciers are melting. I have other slides that get into this even a little bit deeper. But the point is, once those glaciers have melted, the sea level is pretty flat. Here it's accurately measured. Okay? Since 1700, we've had a slight rise. People are making all kinds of predictions about sea level going up 10, 20, 30 meters. But in the last 7,000 years, and when we measure it accurately, there's been really no change. And by the way, I took a graphic here that I know is wrong. Why? Because this little value here incorporates models that are not accurate. My gold rule is to measure tide gauges. Tide gauges that are fixed all over the world. They are accurately measured. There are a number of tide gauges that are well over 100 years old, and they show a linear trend in rise. Linear meaning if the ground where the tide gauge is sinking, then it's going to show sea level rising, but at a linear rate. If the ground is rising, Norway and Alaska, having gotten rid of the weight of the great glaciers, Norway is rising still. People in Norway say, gee, sea level's falling, but it's falling at a very linear rate. The satellites don't do a good job on it, but this still incorporates the satellite data, and it still shows no real rise. This is a video clip that I need to run, okay? And I'm going to show you 1 year's worth of accumulating ice. So here you see, this is in September. In September, we usually have the most open Arctic. So you notice a ship can almost sail through the Arctic. In fact, a number of them have done that, big cargo ships, all right? But then you're going to see that as it gets colder, the Arctic's going to fill. By Christmas time, let's see if I can, nope, wrong slide, guys. There we go. Is it working? There we go. It's supposed to be playing, and it's not playing.
The date's not changing.
It's going, but it's not working.
No, it's working.
And I do not know why.
I don't know why either. It's a September 1. Try doing it off at full screen.
Let's try it one more time.
I've had the same problem.
All right, this is disappointing. I should have tried this out before. What you would have seen, or what you should see, okay, is Hudson Bay filling up with ice, the entirety of the Arctic being covered with ice, and it's seasonal. In the winter, it's all covered with ice, and then it melts again in spring. Maybe some of my other graphics will work.
We'll see.
This one worked in New York. I don't know what happened here. Let's try this one.
Sure.
All right, this one's working. All right. Down here is a year and a month of the year. This is 1989, 1990. Again, warm water comes in here. This blue stuff is called pack ice. It disappears and comes back every year. But the red stuff is the multi-year ice. And that is slowly getting pushed toward the Canadian islands here. 2007, 2008. Now I'm going to start again in 83, 84. Look how much ice in the Arctic was multi-year ice in the mid-80s. And look at what's left. And I feel very bad that the other two graphics did not run. This is 1998, 1999. Again, packed ice forms, disappears, forms, disappears. You would have seen that in the other slide. This is 2010. All right, the last one ended in 2007. There is no multi-year ice left in the Arctic. It is melting that quickly. And that has vast effects on climate. Here's the only equation you're going to see. All right, this shows the seasonality of Arctic ice. This is winter, and this is September. And we've had some records here. 2012, by the way, this the green line here, was the lowest record recorded in our history, ice in the Arctic in September. Why was it low? A storm entered the Arctic Ocean, broke up the floating ice, increased its surface area so that it would melt more, and it did melt. And that ice ends up being gone. Now it refreezes again, but each of these years, these are the averages for the 80s, the 90s, and you notice the trend toward open Arctic is accelerating. Up here, every 10 years, we're losing about 1 million square kilometers of ice. And it's going down and down and down. So this equation, if you want to copy it down, very easy to do. Y is the maximum ice that we will reach in the winter. X is the calendar year. So if you take minus 0.05 times a year, take 2018, 2020, 2080, 2100. This equation will tell you what the maximum ice will be in the winter. It's a linear relationship. It's going down, 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 down. By the time 2100 comes around, there will be these numbers down here will get down to 0. You'll have an open Arctic. Again, the multi-year ice is gone. All you have is pack ice that forms and disappears every year. So try that out, and if you can't write it down, I'll send it to you. It does work. It shows basically that by the year 2300, there will be no ice in the Arctic. And I think it's going to happen a little bit earlier than that because of storm activity and other factors that are going to have a totally open Arctic. And a totally open Arctic changes the meteorology of the whole planet. And we're going to get into that in a minute. This is the depth profile of the Arctic. Here's Greenland, by the way. Here's Spitsbergen. Here's Norway. Spitsbergen is here, sorry. And this is that shallow sill. In the middle is an island called Bear Island. But this is where that warm water streams in. Streams in, melts the ice from underneath. A couple of icebergs shoot out here. Here's a little different profile. Again, this is between Spitsbergen. This is the shallow sill where that water comes in. Here the Arctic is pretty deep.
When you say they melt the ice underneath, how far?
Okay, I need to.
Oh, when you say the warm water comes in and melts the ice underneath, how far down are you talking about?
Oh, it melts it from completely. No, if you have a floating ice cap, which you have every year, once it's winter, everything freezes over. And that's what that one that didn't work was supposed to show you. All right?
He's not talking about the ice on the lake. He's talking about ice shells and sea ice.
Yeah, floating ice, okay? And since the water can get underneath it, it can melt it, and it does. This is the maximum ice extent in the great ice ages. You notice the Arctic itself is open. Now this is something called lake effect snow. I'm glad this thing is working. This happens to be Lake Erie. Wind is blowing across Lake Erie. A big snow plume is coming off. But that's it's a little bit unusual because more snow is coming off that lake than should be coming off that lake, giving its surface area. And I'm going to get into that in a minute. Now I'm going to talk about some of the, and I hope this one runs because this is Galileo's ring and circle. This is some fascinating mathematics involved here. Galileo, in a thought experiment, said, what if I have an annulus, which is this circle right here, and a circle here that had the same area? And what happens if I shrink this at the same rate of the area within here? And what he's saying, and I hope this thing runs.
Try taking it off of full screen.
It's not working.
Try that.
Oh yeah, try taking it off.
Try taking it off full screen because that seems to have.
It only works in presentation mode.
No, it only works in presentation mode.
I mean, I can get out of here and get into my files and show you how it works, and maybe that's worth it. In this case, maybe it is. So excuse me, folks, while I...
And then you could do the other one too.
Okay,
Yeah.
great.
If you can.
Meanwhile, there's some coffee if anybody wants coffee. Would you like some? I can get up and get it for you.
Let's try it again. Let's see if it works here. No. All right, gonna have to get out of PowerPoint to see if I can.
Yeah, you have to go where it's saved, I guess.
Where are those mountains?
Sorry, guys.
It's okay.
The Apollo project. Oh, my tennis game? Oh, how to school. Nice. Oh, she did, okay.
Here we go.
There it is.
Let's see if this works. All right.
I've seen it before, so.
Big professionals that play
All right. So here's Galileo's circle. There we go. Here it is actually working.
Yeah.
You notice the circle is shrinking. The areas are equal all the way down
The line
to a
is up.
simple little point.
Uh-huh.
And Galileo, just going to do it one more time.
Why did he play this thought game?
Galileo used this as proof that a point is equivalent to a line. Because as the area of both disappear down to zero, they are equivalent. And Galileo said that means a single line can have an infinite number of points. And he was right, because points are dimensionless. Let me get out of here and let's see if I can get back into my presentation.
Oh, the other one.
Let me try this guy one more time and see if it works this time. Here we
There it
go.
goes.
All right? I don't know what happened. Again, Christmas time, Hudson Bay gets filled. There it goes.
Oh, yeah.
Now the entire northern hemisphere is coated with ice and snow. And then it begins melting in March. It gets back to what you saw in September. Shows you the extent and the albedo change that happens when we're able to do that. Maybe my next slide will work too. This one should work. There you go. Seasonality in the Arctic. And the same thing comes back another year.
What would the albedo?
And here you go. Down in Antarctica, same thing happens. You have sea ice forming, then it disappears in the Antarctic summer.
There's a gentleman
It comes
with
back.
a question. I'm sorry to interrupt. The question in the back.
Excuse me?
There's a gentleman with a question in
Yes,
the
sir.
back.
Why would the albedo matter when those are the dark months? at the
Because
poles?
they still get sunlight down in Canada. You know, it's not totally dark. It makes it colder. Where I live up in Maine, we're under snow cover. We still get light. But any light that hits the snow in Maine where I live gets bounced off. And it gets bounced off at wavelengths that CO2 can't intercept. So there's it's one of the reasons that there's a multiplier effect when you have a lot of snow on the ground. I'm glad those worked. By the way, in Antarctica, where you see that sea ice shrinking, storms that come around Antarctica then dump snow right onto Antarctica, and guess what? It stays there. It's too cold. It doesn't melt. Now, people telling you Antarctica is going to melt away, I don't think the physics, they have to invent new laws of physics for that to happen.
Excuse me, Tom, why is the Gulf Stream now melting more than it was 100 years ago?
Well, see, no,
Why is it? Is it warmer?
yes, the oceans are warmer. And I'm going to show you that in a minute. I'm going to give you, this is the slide you saw already.
Mm-hmm.
Let that sink in one more time.
Mm-hmm.
Now, you guys are technical experts. You got to figure out why that didn't work.
I have an idea.
All right. Now you stop at 2009. Yeah, just the multi-year ice was right around here. That's it. That's all that's left. Okay. We talked about this already. Depth profile. Okay, here's lake effect snow. And now we're at Galileo circle again. I'm going to change something here. We're going to go to a different kind of diagram. You know, Galileo proved that you can have an infinite number of points on that line. This little semicircle here, you have to imagine this line here extending all the way out to infinity in this direction. And this one all the way out to infinity in the other direction. If you take a ray from this little dot right here and penetrate to each one of these points, there'll be an equivalent point within that circle that will be and only one unique point. That circle will then contain, if you go all the way out to infinity, points in that circle that go all the way out to infinity. So this little piece of line here can have an infinite number of points. So anybody who doesn't understand that, I'll explain it again. Good. Okay. Now you have to imagine that this line becomes a plane and that this semicircle becomes a sphere. It could be as big as a tennis ball. And yet, if I'm in the center of that tennis ball, I can hit every single point in the flat plane through that tennis ball. So there's an infinity number of points in that tennis ball. Why am I talking about infinity? I'm going to talk about Helga von Koch. Koch was a brilliant mathematician. And what he did is he said, I'm going to take a line here and cut it. And this is 1, 2. He's going to cut it in 2 places. And then he's going to build a line here and a line there equal to that line that crossed it. All right? So Koch says, well, this is great. I have a line of length 3, 1, 2, 3, and now I have a line of length 4, 1, 2, 3, 4. So Koch said, what happens if I keep doing this? All right? So I'll tell you where this is going. So Koch builds another little triangle on each of the lines. He builds up like this, each one longer than the other. And it does it again. Here's a little point here, he makes another little triangle. Koch basically said, this line, when I continue doing this process, is going to have infinite length. He did it in a triangle, and he took all 3 sides of the triangle, and it looks something like this. And that's what it looks like. When you iterate and iterate and iterate and iterate, it's called Koch's snowflake. It turns out that this thing now has a perimeter that is infinite. If you keep on doing those lines and go to infinity, and yet the area within this is bound. But it's the infinite nature which is important in understanding how that lake effect snow works. So, if I have a flat lake, and I put waves in that lake, in this case what I have done is I have doubled the surface area of the lake. It's easier to see with triangles here. Each piece of lake here now has double the surface area. The wave and the crest all double the entire surface of the lake. That's important because you can see where I'm going in the next slide. Here's Koch. You keep on doubling the surface of that lake, and you basically, in theory, can get a lake of infinite area. You can't do it. Yes, Carol.
To put this in perspective, the governor of Colorado said that if you took the surface area of all the hills and valleys, that the surface area of Colorado is greater than Texas.
Yes.
So that's a layman's kind
It's the same principle,
yeah.
but you're talking about the physical dimension
Of the
versus the mountains. And by the way, the same thing with the coast of Maine. All the little inlets and stuff like that, they stretch much longer than the coastline of the entire United States.
That's a nice brag, but it may not be true.
Well, we're in Texas now, so
Right.
people can say a lot of things.
So this is the principle behind the lake effect snow. There's also something called molecular bonding. When you have that wave action, instead of a molecule, a water molecule being held by 4 surrounding molecules, they only get held by 3. They're easier to strip and turn into water vapor, which they do. The more an ocean or a lake is riled up with spray and everything, the more water vapor that gets into the earth, into the air. So an ocean on a storm with lake effect has a tremendous surface area. It's not infinite, but it is way, way more than the area of the body of water were it flat. And that's where the lake effect snow becomes powerful. We're going to talk about ocean effect snow in a few minutes. This is supposed to rotate too, and let's see if I can make it work. This time it works. How do you like that? It's a rotation of the Earth, rotates under its atmosphere. So up here the wind is always out of the east, no matter where it is, and it's called the polar easterlies. Let's see if I'll do it again. Maybe it will work this time, maybe it won't. This time it's working. If the Arctic Ocean is open, then you can have the polar easterlies creating that lake effect snow all over the edges of the Arctic Ocean. At the end of each summer, the Arctic jet collapses, comes around the pole. These represent low pressure systems. Here's Greenland, by the way. And they circulate like this. And in the Arctic, they basically pull moisture out of the Arctic Ocean if they have access to the ocean. And if they have access to the ocean, which means the ocean is unfrozen. If you have an ice cap in the winter, there's no access of that moisture to the storms. They have no effect. But if the Arctic is open, they do. So this is again a graphic showing the extent of the great ice ages. Again, the Earth is rotating. Wind is always coming out of the east over an open Arctic Ocean. That can be extraordinarily powerful. Storms come around the Arctic, and by the way the ice ages were formed, the Arctic stayed open. And in staying open, with an open Arctic, you have a moisture source that covered the continents. And by the way, you put and again, I tell you some of my slides are wrong. This one's wrong too. There are other aspects involved. Number one, when you build up snow and ice around the edges of the Arctic, and you have easterlies going like this, you have an uplift effect, which can basically wring snow out of this moisture like a wet towel. You also have fresh water extracted from the Arctic Ocean, meaning the Arctic Ocean is more salty. It's more salty, that means it doesn't freeze. And it stays unfrozen longer. Wave action will prevent new ice from forming. And these storms are very powerful. Now, here's a part that is usually overlooked. As the great ice age is formed, it's like an ice skater spinning and pulling in their arms. They're basically taking equally distributed water around the entire planet and putting it on the axis of rotation of the planet itself. So the planet spins faster. and faster. Yeah, we have evidence of that, and I'm going to show you some of that evidence. And then when the ice melts, and the ice skater lets their arms down, the planet slows. Right now we are in a slow part of that, and I'll show you some graphics about that in a minute too. So here's our lake effect snow. Around the Arctic it's ocean effect snow. And again, because of the increase in surface area, the Arctic Ocean is huge. The amount of volume available for the ocean effect is double, triple, quadruple what it would be from just the ocean itself. So you have a huge ocean supplying moisture. And by the way, when the ice falls on the edge of the Arctic, all it does is move south. And that's why we have a graphic that looks like this. No, I'm okay. Here's the first piece of evidence. When a planet spins faster, winds are increased, Coriolis effects are increased. This shows you on the Antarctic continent, Australian dust. Now, Australian dust never reaches Antarctica these days. But when you have a faster moving planet and higher wind speeds, it ends up on the Antarctic continent. Now, you notice here, this is in depth. We're talking, in other words, you have to dig deep into the Arctic ice to find this Australian dust. But they've done it, and I'll show you where they've done it. They did it here, at the Vostok ice station. The Russians own this ice station. About 20 years ago, through dynamite soundings, they found out that there was a giant lake 2 miles underneath the ice. 2 miles. An unfrozen lake. Maybe it was kept unfrozen because of heat from the Earth's center, who the heck knows. But the lake was unfrozen. The Russians were trying to divest themselves of the legacy of Lysenko. Lysenko is a Russian scientist who basically said Mendelian genetics are wrong. Their adaptive characteristics govern genetics, and he proved it by getting little frogs. And what he would do was paint with India ink on their feet. He'd put little dots, and then he'd raise tadpoles, and lo and behold, the tadpoles came up with dots on their hands. So he said this is adaptive mutations. It turns out later on that he faked it and he put the dots on himself. However, Lysenko became head of the Russian, it's not Bureau of Science, Institute of Science, and Mendelian genetics were ruled out until finally in the 1980s, and the Russians said, hey, you know, we missed the boat here. So the Russians said, hey, we're going to dig into that lake. We're going to find some primordial bacteria, because nobody has been in that lake for thousands and maybe millions of years, and we're going to contribute to genetics. So they said, okay, we're going to start drilling. The Americans and the French and the British said, don't do that. And they said, why shouldn't we do that? He said, well, do what we did in Greenland. Take ice cores, punch an ice core down, and look at what you're getting in the ice cores. And they're getting a lot of stuff. They got the Australian dust out of there that you saw before. Come on, guys, here we go. This is the Vostok ice station. It says, Vostok welcomes you. Okay? It's pretty cold there. It's 60, 70 below zero. I'm not so sure how welcome it is. And by the way, this is the rig that they drilled in. This is how they got their cores. This is an aerial view of the same place. Totally desolate, by the way. This is what ice core looks like. It's a plastic sheath. Now, if I had my own car here, I always carry one of these in my trunk. It's a nice prop. It's an actual ice core body. But you have to look at it here and just say, this would they take your magic marker and they write down how deep it was and what they got out. The Americans did this in Greenland because we wanted to find out whether we could land planes on the ice cap. And you have to test the strength of the ice cap to make sure you can do that. And And it did, and we did do that in the Second World War. At the end of this, ask me a question about Glacier Girl, and I'll tell you about one of those landings that went the other way.
Oh.
Now, this is what they found out. The Vostok ice cores, this is the present right here. And you saw, hey, look at this. As they went down into the ice, they were able to see and check, taking slices out of the ice. They could tell what the carbon dioxide levels were. They could tell the ratio of oxygen 16 to oxygen 18. Oxygen 18 is basically heavy oxygen, has 2 extra neutrons. If you had a room of oxygen 18, you were breathing it, you'd say everything is fine. But it takes heat energy to kick oxygen 18 out of the oceans, and it does so when it's warm. And when it's cold, it doesn't happen. So they had a pretty good idea of what the temperature was. And you notice each of the peaks that we've had here, by the way, it only goes back around 400,000 years, because that's when they hit the lake. And the Russians didn't listen to me. I had sent the UN a letter suggesting that they take a stainless steel sterilized needle of about 20 meters and then punch into the lake so as not to contaminate it. The Russians just drilled into it. I don't. They took up the material. I don't think they contaminated it too much. But, you know, each of these previous interglacials was warmer than today. We haven't gotten there yet. And yet we have a relatively flat period here. Keep in mind, this is 5,000 years. All right? No, actually, it's 10,000 years. So for the last 10,000 years, it's been pretty stable in temperatures. And yet the other ones are all peaks. Why is that? We're going to get into that, because I happen to believe that this particular graphic is incorrect. Remember, there's a few other ones that aren't right either. Oh, by the way, you notice the CO2 levels lag. In other words, the temperature goes up first, then CO2 follows. When the temperatures decline first, CO2 then follows. The CO2 is not a leading indicator of temperature, it's actually a lagging indicator. And how it happens, this is, at least this one works, this is molecular motion. The oceans have a density of about 800 times that of the air. So, and heat is molecular motion. So when the oceans warm, the planet warms. If these happen to be Brownian motion, if you have more heat, they increase the heat in the ocean, they kick out the heavier dissolved CO2 molecules. When the oceans cool, the molecular motion slows down, they can reabsorb the CO2. And that's what we see in the Vostok graphics. And we see that the CO2 tracks very, very well. But again, the temperature always goes first, either up or down. Okay, this is a little better graphic. You can see that 20,000 years ago, we were at maximum ice. You need to go through? Okay. And then the ice starts melting. And it melts and melts and melts, and then finally it stops melting because there's no more ice to melt. And we have kind of flattened out. Remember what I said about the rotation of the Earth? Speeding up when we have maximum ice, and then slowing down when we don't. Well, the future, and this is wrong too, by the way, but this is a very simplified version of what it's like. When we would build up more ice, when the Arctic opens up, by the way, and that equation will show you that the Arctic will definitely be open by 2300. I think earlier because of storm action. We begin a new onset of glaciation. It looks like this. The planet will start spinning faster, and we have that off again, on again spinning. This is something that happened about 2 or 3 years ago. In 2012, we had a blob of warm air, came up actually from Texas. Across the Northeast, we had record heat in the Northeast, but it settled over Greenland. And it settled over Greenland and passed and melted a huge chunk of Greenland's surface. It was an overall melt. The least that was melted was 2 inches, in some places 6 inches of ice, all over the continent. Now you think about that. By the way, 6 weeks later, you had massive snow in Greenland. You picked up 3 or 4 feet, and the event disappeared. But if you're taking an ice core in Greenland, you have lost the data that was in that melt. As the planet warms, we're going to see more and more of this happening. And the planet will be getting warmer. The planet as a whole. It has nothing to do with humans or anything else like that. It has got to do with the fact that sunlight gets absorbed by the oceans, and the oceans retain heat. When you fly over the ocean looks dark and black because it's absorbing all the sunlight that's hitting it. If there are clouds, it gets reflected. And there's some, maybe I'll talk about Svenssmak's theory later on, but it's not part of this lecture. Increase the clouds, you're going to increase the reflectivity. But on balance, the oceans are getting warmer and they are melting that ice cap relentlessly. They've already gotten rid of the multi-year ice. So we're going to have more of these episodes in Greenland. We are probably going to start getting them in Antarctica. We haven't had one yet. But when you do get one, you lose the data that was in that. And that's very, very important. Why? Because it is very possible that our graphics are incorrect. Remember, the previous ice ages peaked? What if they have a flat area like we have right now? And yet the melting that occurs as the planet warms wipes out the data and turns it back into a peak. Which means that our dating of the ice cores probably is incorrect. In other words, they are probably separated by much more time, and these periodic meltings that we have at the peaks have wiped out that data. So our understanding of the glacial cycles is probably not perfect yet. We have a ways to go. This is the Mid-Atlantic Ridge. I won't get into how this started, but it's got to do with the dinosaur meteor. Once it hit the Earth, things changed, and that's part of a different discussion. But Africa and South America, Europe and North America started separating very fast at first, and now very, very little, maybe 3 inches a century at this point. But they separate along this tectonic ridge, and that ridge is slowly moving apart. There are a couple of places where the separation actually hits the surface, up here in Iceland, for instance. In fact, here is in Iceland, you can actually walk on the split of the Mid-Atlantic Ridge, and the Icelanders take tourists there. Yeah.
Oh.
This is the Western side, and this is the European side.
Wow.
And it's being split. Now, no volcano here. However, let's see if I can get this guy to move. It's supposed to move here. There we go. This one was working. Underneath the ocean, on the Mid-Atlantic Ridge, you have stuff like this happening. That happens off the coast of Iceland too, by the way. You have the underwater volcanoes. It's the first time they've actually gotten stuff to photograph. It's fascinating.
Yeah.
And yet, you don't. This is not smoke, by the way. This is just ash that comes into the ocean. Let's try it one more time if I can do that.
So
You have to
that
think
is
about
an underwater volcanic eruption?
Yes.
Huh.
However, it is the separation of the Mid-Atlantic Ridge. This happens along the entire ridge, not every day, not every month, but in South America 1 year, in Iceland another year. Iceland, of course, they go on top, and this is what it looks like. The Mid-Atlantic Ridge basically you get these little tiny volcanoes sending up lava, and the ridge opens up and spreads. This is fast motion, okay? The process you're looking at here takes thousands of years. This is Eyjafjallajökull. I flew over this in 1999. This picture I took. 10 years later, it blew its top. It's on the Mid-Atlantic Ridge. And disrupted air traffic. Beautiful volcano. This is what it looks like after it erupted. I didn't take this picture.
What year was that?
This was around 2008. Around. I may be off by a year or so. Relatively recent.
Yeah, it was dramatic.
Big volcano.
Yeah.
Planes flying through volcanoes lose their engines.
Yeah. Oh, wow.
All right. We had a KLM airliner flew over Aguan in Indonesia in 1962, and all 4 engines shut down. You imagine the panic that the pilots had. It was nighttime. They couldn't even see it. They didn't even know they were doing this.
Wow.
Anyway, they flew out of it. They were able to do restarts, and the plane didn't crash. But then, you know, the air traffic controls say, that's it, you don't fly over here anymore. And unfortunately, Iceland is in a flyway from Europe. So European air traffic to North America was disrupted for about a month or so.
I remember that. Yeah, all over Europe.
That's right. That's right. Anyway, here's your seafloor going up again. Well, what happens to this crust when it comes out? This is what the magna would look like. All right, you imagine a plate of magna coming up. And yet, within this rock, you have iron particles and other things that are magnetic, which are pointing in all different directions. So what do? They capture the magnetic field of the Earth and orient themselves to that field as the volcanic lava comes up. So here you have the arrow of the magnetic field pointing down, and the arrows line up like this according to the field. And then you have a change in the magnetic field, and you're going to notice here now the arrows are a little bit different. They're neutral, and then they're going to line up in a different direction as more lava comes up. And this is called the piano key effect. Why? Because it looks like keys on a piano. And you can take a look at that seafloor spreading, and we can test which direction the Earth's magnetism held at that time. This is what it looks like off the coast of Iceland, and you notice the keys aren't exactly the same. Some of them are bigger eruptions, some of them are smaller, but they do have a magnetic signature as to when they came up. So here you have a diagram of the Earth's surface, the kind of fluid outer core and a solid inner core. The solid inner core is almost all iron. And when I was a kid, the physics teachers used to tell us that the Earth's magnetic field was caused by currents within the outer core that were then basically creating field lines coming out. Well, things are a little bit different. Remember I talked about the fact that the Earth, in an ice age, started rotating much faster. And then, as the ice age ended, the Earth would slow down. Well, if you take a look at the history we have, if you understand that the Earth is now slowing down because we have come out of that ice age, what you would expect, if the core is not solidly linked to the surface of the Earth, and the viscosity is enormous, by the way, because you have millions and millions of tons of pressure, and yet you could assume that at this point the core would be spinning faster than the surface. And an electrical engineer would say that this is the rotor-stator effect, where you have the magnetic center, the iron center, and the lighter elements, the coppers and the zincs in the outer mantle. And guess what? Some researchers at Columbia, Song and Richardson, 10 years ago, found that that was exactly happening. That the center of the Earth was actually rotating faster than the surface. It's at the right time, too.
Tom, you said the Earth is slowing down because we've
We melted the ice.
Because we've come out of the Ice Age?
Right. In other words, that ice that used to be at the axis of rotation of the planet and making the planet move faster. Mm-hmm. Now that the ice skater has spread out their arms and that ice is now distributed now in the oceans all over the planet slows down.
That has to do with where we are in positioning.
This is where we are right now today. All right, we're right up here. We're 0 thousands of years ago. Okay, so the Earth has slowed down considerably, and yet the core is still rotating faster. Now, when we go into the next ice age, once we have that open Arctic and we start building up a lot of snow, the planet's going to spin faster. It's going to overtake the core. And when it does, the rotor stator means flip on the magnetic field. When the surface goes faster than the core, you have a different north-south orientation.
But what's causing that?
The ice age is essentially causing it. The fact that we have an iron core in the middle of the planet means that we have the ability to generate a powerful magnetic field because the entire planet is in effect an electric motor. You let that sink in a little bit. And if you change the speed of the core versus the surface, you're going to change the polarity of the magnetic field. Here's the danger part. At one point, when we're at the point where the core is finally going to get overtaken by the surface as we start speeding up the planet, the core is going to we are going to have a zeroing out of the magnetic field. That's going to let all kinds of cosmic rays come in. As you're developing a new ice age, that's exactly what's going to make the planet even colder. Because according to Svensmark and other theoreticians, the cosmic rays coming in will basically form nuclei for clouds to condense upon. More clouds, you get more reflectivity, colder planet, makes it even colder. Meanwhile, the Earth is still spinning. Open Arctic creates all kinds of ice, and we have 4 or 5 miles deep ice in Norway. It's a huge amount of volume of ice, and ice is heavy, by the way. If I have a cubic meter of ice, it weighs a ton. If it was water, it would be 2,240 pounds. Okay, the ice is a little bit lighter than water. Imagine sticking these 1-ton blocks 2, 3, and 4 miles high on the axis of rotation of the planet. It has to make the surface move faster. And as long as the core rotates at a different, has a differential rotation than the surface, we're going to have a magnetic field, and the magnetic field will flip. Well, guess what? The piano key effect shows us that that's exactly what happens. Because as the magma comes up, the polarity is reversed. Those are the keys in the piano. They're polarity reversals. And where would they be coming from? Here they are again. Here's some other evidence. We have been adding leap seconds because the Earth is gradually slowing because of the attraction of the moon. But all of a sudden, we have a more open Arctic now. You saw that in the earlier slides. Our Arctic is more open. We are getting more snow deposited in Siberia. 2 years ago, when I spoke in China, I flew over Siberia in October when there was not supposed to be any snow yet. It was covered with snow because the Arctic was really open. They had the coldest winter on record, according to the Chinese anyway. So northern Siberia has snow on the edges, on the axis of rotation. You do that each of these years as the planet begins to lose ice in the Arctic and gains ice on land. Rotation speeds up. So what are we doing? We are adding fewer leap seconds. At one point or another, this curve would show you, and this is probably wrong. It's probably 2038, 2048. We are finally going to even out and start subtracting leap seconds, which means that the Earth is going to start spinning faster. The trend is already there. Yes, sir.
So what role has man played in this?
None.
None. So
No.
it's inevitable.
Yes, we have a role. We are observing this and learning from it. And I think that's very good for people to do. Yes, ma'am.
Yeah, when you say what role man has, how about like these weather research? How about these weather research stations that they have such a part? And not only our country, but other countries are experimenting with being able to control or change the weather.
Well, we're not going to change the weather, right? I mean, I've heard people talk about that. I don't buy it. There are people who believe you could squeeze more rain out of relatively dry air. And they've done experiments in Libya, I think some in Israel, some in Saudi Arabia, where they could use a lot of water, or certainly more than they're getting. Our ability to change things is not as much as people would hope. And some of the weather stations you talked about are based in little villages in Russia and Canada, where you have the effect of a little mini urban heat island. And you put lots of these stations in these villages and you enter them into a temperature grid, and lo and behold, it looks like the Earth is really warming relatively quickly. But it's not, because the vast open areas really aren't. It's the ocean warming that's important. It's the ocean warming that's going to melt that ice and snow in the Arctic, and then result in the increase of snow, including massive glaciation where we have it here. Yes, sir?
But sir, everybody knows from direct observation that if you put a hairdryer and focus that hot airflow on a pot of water, it'll boil in no time flat. I mean, it'll really warm up that water right away,
Well,
despite air being less dense than water. Right?
We've had some interesting situations where they put a temperature sensor on an airport where the exhaust for the jet engines of planes taking off happens to spike the temperatures, and they say, hey, we're having record temperatures today. They did that in Baltimore, by the way. Yes, sir.
These leap seconds are per day?
No. This is by year. This is 1965, 70. These are the years that we were adding leap seconds. But now, as the Arctic is more open, we are basically changing the spin rate of the Earth. The time between the leap seconds is getting longer and longer and longer.
So it's a matter of seconds per year.
That's right. And there's some years that we don't put a second in there at all. And they're spreading out. It's very, very slow starting, but the fact is the process has started. And that's a that's a trend you get out of it. Again, leap seconds down here are going to be subtracted. As the Earth spins faster and faster and faster, we want to keep the days in right. We're going to be taking them out. Yes, sir?
Serious question this time.
They're all serious.
All right. Is it known or estimated how much heat is being added directly to the ocean depths by volcanic activity?
Not enough to make a big difference. I think that big orange ball in the sky is providing almost all the heat that the oceans get.
Okay.
All right?
Thank you.
There's a question
Okay.
here.
Back to...
Yeah,
Yes, sir.
I actually have a couple questions. Are you saying the speed of the core is constant?
Can you speak up?
Is the speed of the core constant, or does that change?
No. Let me get back here again. If you have the core being dragged, literally, by the surface of the Earth, as the surface speeds up, the core lags behind the surface, all right? So as the planet goes faster and faster and faster, the core begins to catch up. When the ice age is at its peak and then starts melting, and the reason it melts, by the way, is that At one point or another, we lose so much sea level that the warm water can't get into the Arctic anymore, because the ocean is basically captured and put back on land. So the sea levels drop, the ice can't get warmed, can't get melted, and the Arctic Ocean flash freezes over and never, at least in another 100,000 years, opens up. And then all the ice can do is melt. And when that ice melts, the planet begins to slow. Now the core has been catching up to the surface. Finally, the planet slows down so much that the core is now rotating faster. Magnetic field flips, and then, like today, we notice that the core is in fact still rotating faster than the surface, but it's slowing down too. And by the way these guys did it, they went to New Zealand and they were able to take sonic readings of earthquakes in Alaska through the center of the earth, and they could tell when pieces of the core got so that they could get a good signal through, and then they were blocked. And that way they were able to tell that the core in fact was moving faster than the surface. It's totally counterintuitive. We didn't know that before. And the rotor-stator effect, really, I mean, the takeaway from this is that it's the ice ages themselves that generate the magnetic field differences that we see in the piano key effect, and not the other way around. It's stunning if you think about it. Stunning
and
to
they're
me anyway.
actually propelling the speed of the rotation of the Earth.
Actually, one of my slides that I didn't put in here is a little demo I have, a little electric motor. I would spin it with my hands and attach the electrodes to a voltmeter, and when I spin the motor, you can see the voltage go up, all right?
Right.
And you can see in the core too, creates a magnetic field. So let's get back to where I was here.
I have a question.
Yes, sir.
The moon is said that is receding from the Earth, and the moon also is having some effect on the gravitation of the Earth.
Now, you gotta speak a little bit louder.
The moon is receding away from the Earth.
And is in fact slowing the Earth
and is
down.
slowing down.
Right.
So you have two forces that are in opposition. One
That's
is
correct.
adding, speeding, and the other one slowing down. So which one wins?
In the development of the ice ages, there is so much mass being transferred to the axis of rotation that the Earth wins. However, the next time when the ice melts, the moon is a little bit ahead. All right, so the moon does have that effect. In fact, one of the neat things is, remember I said that the core is still spinning faster. Now you have provided evidence for that, because the magnetic field of the Earth is in fact weakening, and we can track that weakening. And that's exactly what you would predict if you had a slowing or catching up of the core to the speed of the surface. Eventually it will. But the magnetic field is already weakening. By the way, the guy here wrote a paper, quite an intriguing paper, which in fact has that data about the magnetic field getting weaker. I've got to work with him on getting some stuff.
My other question was that obviously we have another heavenly body that changes magnetic field every 11 years, and that is the sun.
Yes.
And it does not have any polar regions. So I understand where you're coming from. I'm going to give a very serious thought about it, but the fact that the sun does not have any cold masses,
that's correct.
Yet it does change magnetic fields regularly.
Well, every 22 years, the sun's magnetic field flips. All right, it's an 11-year cycle, and those cycles are getting weaker, by the way. But the Earth's magnetic field in power dwarfs the sun's magnetic field in relation to its distance from the sun. The sun's magnetic field is very powerful close to the sun. Out here, it protects us from cosmic rays.
Right.
when the Earth experiences a low solar sunspot cycle, when the sun is in a low, we get more cosmic rays here.
True.
And that trend has been increasing because the power of the sun itself has been decreasing. That's another set of slides.
Or because the Earth's magnetic field is weakening and is allowing more cosmic rays in.
That's part of the equation too. You're right. And by the way, when the synchronous asynchronous rotation flips on Earth, we have no magnetic field for a while, and we get bathed in cosmic rays. So, one of the proposals to control this was for humans to build a dam across the Bear Island Strait. And this is a dam that they have in Holland, where they can open and close the floodgates. And in theory, we could decide to stop ocean currents from coming into the Arctic, allowing the Arctic to stay frozen, and end the onset of an ice age. All right? Now, but wait a second.
The weather in Ireland.
This is the strait that it would be done. This is Spitsbergen. And by the way, Spitsbergen means spiky mountains in German. Spitsbergen.
And where
Okay?
is that, though?
And these are the spiky mountains in Spitsbergen.
And what exact area is that?
Spitsbergen is an island, now it's called Svalbard, the Norwegian zone. I showed it to you on the earlier graphics.
Okay, that's fine.
It's between Greenland and Norway. This is the northern part of Norway called Nordkapp. Bear Island is right in the middle. So here's Spitsbergen, here's Bear Island, and here's Norway. The proposal is to build a dam across this strait here and control the warm water from coming in. The problem is, I mean, what's that?
What's the width?
How long would that be? How many
Oh,
miles?
150 miles here, 200 miles here.
Oh.
We could do it. However, should we do it? And the answer, in my view, the answer is no. Because if we stop the ice age from forming, eventually the core will slow down and match the surface. We kill the magnetic field, and it stays killed.
Would that really stop the ice age from forming by stopping warm water
Yes.
from coming?
Yes, because then the Arctic will freeze over, Keisha. And if it freezes over, there's no moisture source. And by the way, that happened.
That's the only way that the Arctic can freeze over is by that water, warm water.
No. It freezes over every winter.
Right.
All right? But if you notice from that graphic and that equation I gave you, the freezing over process is lessening and lessening and lessening. All right? Once the Arctic is open, ice age begins. About 300 years from now. I think actually about 200 years from now, but that's a
Oh,
different
that's
deal.
soon? That's pretty soon.
Work on the equation, put the numbers in and see how it works out. Right?
I'll let you do that.
No.
So, you know, the movies try to present that polar flips happen in 24 hours, and there's a mass kill over, you know, like the movies like 2012 and so forth. And everything I've read shows these things happen over thousands of years.
That's right.
So, I mean...
Keep in mind, the first snowflakes will fall, if I can back up a little bit here, to start an ice age. This is a 20,000 year cycle here. And yet this is wrong. Why? Because the Vostok ice cores, I get back to the Vostok graph. Where are you?
You're back.
Yeah, there it is. Because you notice there are spikes here. Here you have the first cooling, okay? The first ice forms. Arctic is wide open. Planet spins faster. Snow is falling all around the Arctic. It gets cold fast, and all of a sudden it stops. Why does it stop? Because the Arctic is frozen over. It gets warmer again. See, that's why I said it. The other graphic totally oversimplified things.
Can you...
And this can go back, and the interesting thing is, if you ever heard of Milankovitch and the precession of the equinoxes...
Can you put that graph on top of your keyboard graph?
Yeah,
Does
put it
those
on.
fit?
No, they're plotted different ways.
would there be a way to do that, to see how?
No, the dating is different, but the point I'm trying to make here is that magnetic fields, I'm sure, have reversed right in here, right? We flip down here, we generate a very fast-moving Earth, then the core is catching up, then it warms up.
You're saying it reversed because of that spike?
Yes.
Okay.
And it does it on the precession of the equinoxes is the major effect that is visible in the Vostok ice cores. You know, Milankovitch has different things, but precession is really in there. Why? Because at some time of the year, the Pacific Ocean gets in much, much more sunlight when it is closer to the sun. And right now, that's exactly what it is, which is why the oceans are warming. The oceans are warming. Yes, sir?
He asked a question, and I don't think that I quite got the answer to his question. Is the Earth core heating up or cooling down?
Staying about the same, because it is basically totally compressed iron. The entire interior of the Earth is hot.
Yeah.
The lower you get, the more compression you get. I don't think, now this is me thinking, okay, that there is any great variation in the core itself. We don't see a lot of temperature variation even close to the surface where the magma comes out. Magma is enough for molten rock, and that's it.
Have you seen any information about the shape of the core of the Earth? Is it?
It's lumpy. It's lumpy, and that's how Soon and Richard. Yeah. Not only that, it's lumpy in the sense that they were able to see through parts of it, and then the core moves, and then you can't see through it. That's how they were able to figure it out.
Okay.
They don't teach you that in school. Well, they only figured it out later.
Yeah, I guess so.
Let me get back here where I
Are these
was.
questions because the people asking them think that we are warming up the planet, humans?
Oh, absolutely not.
I didn't hear what you said.
He said, are these questions because the people asking them think that we humans are warming up the planet?
Well, I will be very, very candid with you. Humans are not warming up the planet. Humans are adding a little CO2. CO2 makes the plants grow very nicely.
Yes.
You know,
you're in the crowd who does not believe that human beings
but the sun is warming up the planet.
Yes.
It has, and
sure is. You go
and thank
outside.
goodness we'll do so for many, many years. However, once we open up the Arctic, allow that lake effect over an infinitely big Arctic Ocean to put enormous amounts of ocean water on the axis of rotation, planet goes up, sea level drops, and yes, there are effects. Building that dam might do it, but I think it is a disaster if we do that. We would basically kill the magnetic field. The thesis I'm talking about here is that the magnetic field's strength and direction is caused by the ebb and flow of the ice ages and its effect on the rotation of the planet. It is something that is totally against all of my own prior thinking. But once Song and Richards, and Song and Richards is a paper that you guys ought to read if you'd like, and I'll send you S-O-N-G, like you're singing a song.
What's the
they're
title?
from Columbia.
What's the topic?
I don't have a title off the top of my head, but I don't know, I can put it on our website.
Tom, what is the maximum speed differential between the surface and the core?
What is the speed differential between the surface and the core? Maximum speed, yes.
Song and Richards said that the core is making 1/4 turn, I think, per 10 years. I have to review the paper and get it myself. I'm not quite sure of that answer. But it is a substantial difference, enough to create this magnetic field. But again, the Earth is slowing down. The core is also now going to be slowing down. The magnetic field is going to be decreasing slowly, and that has already been seen. Yes, sir.
I was just wondering, your description of that dam, is there a way that you could build some adjustments into it so it wouldn't be a permanent blockage?
Yes. The picture of the dam I showed you is one that you can open and close.
Right.
So we could decide that at one point or another we want to create a lot of fresh water on the top of the world. In ice you can do that. Then you say, hey, let's leave a dam open for a while and let the ice melt, build up the ice and snow, and get that fresh water and send it down to the deserts. It is something that we could do. The question is if it's something that we should do. And because of
a lot of electricity too.
Well, you could. Keep in mind, wind speeds increase like they did in Australia. So that would make wind turbines very efficient. Yes, Alex? Yes.
You build that dam and you close it. Now all the water on one side of it freezes. Now you're going to open that dam with one side of it frozen?
Sure. That's the only way you'll get warm water to get in there.
Well, I just wondered how you open it. Got water frozen right against it.
No. Keep in mind that the dam here, the one you see is actually here designed to prevent flooding in the Netherlands if they have big ocean storms. This is the mouth of the Rhine River.
Yeah, they don't have the ice problem.
They do not have an ice problem. Yes, Carol?
Well, the current is coming up from the Gulf, it crosses over to Ireland and goes up to that Bear Mountain. If you put a dam there, that Gulf, that elevator of ocean water is going to hit, where is it going to go?
It's going to go right down to Europe.
Oh, and you think it'll just turn and go down?
Yeah, that's exactly.
You're trying to flood out Europe?
It won't flood Europe. However, it'll make Europe even warmer than today. So Europe will warm. Norway will love it.
But then the water's not going into the Arctic and coming down that dark blue trench and coming back down to...
Look, there is going to be water going in and out of that trench. Keep in mind, the ocean is three-dimensional. You have surface water going in one direction, you're going to have cold water going in the other direction. The ocean circulation won't stop, you know.
Okay.
Yes, Keisha?
Okay, so I want you to talk, you've touched on it, but there's a relationship I think you could develop, I want to develop a little bit more, which is I still don't see where the cosmic relationship is coming in, because we've talked about the Earth core, we've talked about that process in relationship to the
all right, so
ice
here is the...
But where's the cosmic
this is
solar...
what you... All right, this is what you need to do, all right? On my website, there's a page called a media page. The last presentation on my media page gets deeply into the solar relationship to cosmic rays. I've got some stunning graphics there.
And how that's melting the ice.
Well, it's not melting the ice. The fact is the cosmic ray increase is allowing more clouds to form and actually making the Earth a bit cooler. That's covered in that presentation. So here's the hint. The website is called colderside.com. Go to the media page. You go above the last presentation and you get a lecture of me telling us why we have to go to Mars. And that's okay. I do a lot of things.
What about the relationship between of the Earth to the galaxy and the motion of the galaxy?
The Earth's and the solar system's motion through the galaxy also is impacted, or we get impacted by cosmic rays. And the way it happens is like this. We are in what used to be an outer arm of the galaxy. Now we have found out, by the way, that the galaxy extends a lot further. And we have found stars far more distant that are still under the influence of the galaxy. So we're not in the outer arm anymore. We're kind of in one of the middle arms. But we're not just static in the arm. We undulate in and out of that, like a seesaw almost, or a wave. When we are on the outside, we are then influenced by cosmic rays that come in across the entire galaxy. Right now, when we're in the galaxy, there are stars and suns and nebula and cosmic dust that don't allow the cosmic rays to get to it. They're still getting here. But once you have crossed and are up from the surface, you get them from across the entire galaxy. We then get bathed in cosmic rays until we are now shielded in. We haven't pierced the upper level yet. Now, I don't know what your concept of up and down is, because up in the galaxy, if you look at it backwards, is down. But I think the real way of looking at it is in and out of the galaxy, in and out of the galactic plane. And that motion does happen, and it happens at about 100,000 or so year intervals. And you see the Bostrick cycle is at 100,000 year intervals, you know? So the bathing of cosmic rays on the planet probably adds to cloud formation that makes the planet even colder during the Ice Age. And then we come out of it as we melt. There are so many interesting, fascinating relationships, and some of them are coincidental, some of them are totally meaningless. And you know, the fact is, if you think about it, we are the only species on this planet that has a ghost of a chance of understanding any of this stuff. You think an insect with its antenna is looking at the galaxy and figuring out what the heck is going on, or knows what an ice age is,
They respond?
or even knows what an electric motor is, unless it's an electric fly swatter that gets them, you know. Really, I think we need to celebrate our intelligence, because it's the only thing that really works here.
We are the only species who can leave this planet.
Yes, of course. The
The
only other species that have left the planet are like half the monkey that we sent up on one of the first rockets, and you know, people with real guts like Walt, and we sent him up. But you know, no other species can do this kind of thing. None.
I'm sure some of the roaches made it to space.
Some of the roaches. They may have been on the tail of the rocket going up, but by the time they got in there,
that was in with the people's luggage.
Bed bugs on stage. Watch out.
I got another question.
But, yes, go ahead.
Okay, so Nir Shaviv and Sven Smart co-authored a paper.
Louder, please. You got. They want to hear you back there too.
Shaviv and Sven Smart co-authored a paper talking about celestial driver of the Phanerozoic era, where they said this argument that it's the motion above and through the arms and the plane of the galaxy that's the primary driver of ice house and greenhouse Earth. And it sounds like you're saying that may have an effect and making it more extreme one way or the other, but that the primary, are you asserting that the primary driver of climate change on Earth is this the speed and the shifting speed of the crust from the
That's
core?
a primary driver of the magnetic field, but not necessarily has nothing to do with us getting in and out of the plane of the galaxy.
Where the magnetic field would be as a primary buffer, along with the sun, of cosmic ray influx.
The sun is actually a larger buffer for our whole section of our planetary system for cosmic rays.
So you're instead of trying to come up with a primary mechanism, you're simply adding another dynamic factor to the body of the
There are lots of factors, and I haven't even mentioned all of them.
Yeah, we wanted to hear the rest of your presentation.
Yeah, are there more slides that we should get through?
What's that?
Are there more slides that?
No, this is pretty much the end of it, because I'm summing up here.
Okay.
I mean, of all the things that, this is my concluding slide, all right? We need to do research to solve real problems, not to have nations develop tax revenue. And that's what the whole CO2 meme is all about. It's trying to tax oil companies, not you, not people, But oil companies, it's a backdoor tax. If the politicians in Europe, and they're the ones I think are most to blame, but we have it here too, the politicians don't want to tell people, oh, we're going to raise our tax rates. But if they say we're going to tax oil companies, guess who pays the increase in costs?
Yeah.
You do. It's a backdoor tax. And that seems to be the IPC's raison d'etre. All right? Raise taxes without really admitting that they're doing it. So we need research to see if, in fact, the other Vostok data is correct, that these interglacials are really longer, and then the evidence of them disappears, and we get these spiky things in the last ice ages because we have melted the evidence in between. And I really believe it has happened. The evidence was very clear in Greenland how much data we lost, and we haven't even started that process in Antarctica yet. And again, each of the other interglacials was warmer than ours. We haven't gotten there yet. We're still on the way. You know, here's where we are now. We know about the asynchronous rotation of the core and the surface, and that's something that a dozen years ago nobody knew about. They theorized it might be there, but now we actually know what's happening. And can we manage CO2? Is that a solution? No, it's not. And building the dam probably isn't either. It could have disastrous consequences. So the point is, this is what we need to do for the research. We need to look into it, look into the possibility. Maybe we should have a dam we can open and close, but then we got to make sure that we do open and close it and don't leave it in one position. Yes, sir. Got to speak louder.
What can you say about researching this realm of magnetic fields on the moon, on Mars? I mean, just a historical standpoint.
Okay. This is why I'm a big fan of NASA. All right, and you'll get that if you go to the presentation above it. Why we go to Mars, or why we should go to Mars. I don't think we should go to Mars. I think we should go to Phobos. And Phobos is Phobos is the fast-moving inner moon of Mars. Goes around the planet 3 times in one day, very fast. Rises and sets 3 times. If we go to Phobos, we don't need that much fuel, because as you put the brakes on when you get close to Mars, you're going to catch up to that fast-moving moon. The geology of Phobos is fascinating. I'm going to try to get Jack Schmidt excited about this. He's a geologist, all right? You stay on Phobos for about a year or so, and then when you come back, you go off on the other side of the planet. You get a boost from that planet, so you don't need that much fuel to get back to Earth. Right now, we can't get anybody off the surface of Mars yet. If you ever been down to Cape Kennedy, you see the gantry cranes and the fuel depots and all the things that we need to get someone off the planet. It's enormous. It's an infrastructure we don't have on Mars. So we can get off of Phobos, because gravity there is pretty light. And the fact is, and I make this point in the presentation too, I don't want to go to Mars. I don't want to go to Phobos. I want to develop the technology that gets us there. Because what we did in Apollo is we developed technology that was used all over the world. There isn't a job on this planet that is not affected by what we were able to accomplish in Apollo. And it's stunning. And one of the things I mentioned in our presentation too is once I was giving this talk somewhere, and some guy raises his hand and says, well, what about the guy digging ditches? How's he getting helped? And my answer was, one of the few times I could think fast on my feet, I said, look at the titanium coating on his shovel and tell me the space program hasn't helped him do his job better.
Right.
And every job, go home and look at what your life is like. I see cell phones on the table. None of that would have happened without the space program and miniaturization. I go to Andy Anderson here. I hang around there once in a while for them to get me better. And the medical technology that exists today could not have and would not have existed were it not for what the Apollo program did for humanity. Yeah, yes, Walt. He's one of the guys that did it too, by the way. Right.
Thanks, Walt.
I tell them about how we got the computers started on Apollo.
With the women.
And the computer for the command module, which has portions of that first one. But we had a computer on there. It was necessary for starfishes and the like, and it was about this size, and it weighed 40 pounds. And anybody care to guess how much storage we had, electronics, in that particular?
10K.
No, it was like 160.
160 what?
4,000.
Of what?
No, just
Kilobytes?
No. I thought it was just like not over 100,000 bytes.
You must know. No, we have 40 kilobytes.
40 kilobytes.
K, 4K, not meg.
And that 40 kilobytes went to the moon and back and landing and things like that.
And by the way,
That's less than 100,000.
when Armstrong was landing, he by accident overloaded the computer and had to manually override it to make a safe landing.
Wow.
He had 20 seconds left of fuel. That was it.
Right, wow.
So anyway, the cell phone here has way more power. A programmable calculator has more power.
Different world.
However, it helped spur the development that got us to where we are today. Nothing that we touch today has has not been influenced by the Apollo program. That's why I'm such a big favor. Yeah.
So I had one more point of information they may not know about, because what's the level of CO2 in the atmosphere?
Well, 409 parts per million right now.
400
Yeah. What was it in your
400
capsule?
parts per million. Well, back in Apollo, we had an alarm system in there. The CO2, of course, we were 100% oxygen. We had to keep the CO2 units changed. We had an alarm that went off. In the 11 days of Apollo 7, the alarm did go off one time. Does anybody have any idea what the level was that made the alarm go off?
800.
5,000.
10,000.
Oh, it was 3,000. It did go off once. And when you got to the shuttle, the alarm system, I don't know if they changed it in or not, the alarm system went off at 7,000 parts per million. I'm only mentioning this so you understand how stupid it is, some of the concerns that were being given today. And I think that now in the space station, I can't say for sure, but I think they've got it 5,000 parts per million.
Yeah, submarines have a 5,000 also limit.
Well, I think it's more than that. You know, the submarine launched ballistic missiles, they can stay submerged for like 4 months, 100% oxygen, scrub the CO2, their alarm goes off at 8,000 parts per million. All I'm saying is some of this nonsense that we have going on in our society today, we ought to find some ways of stopping that stupid thing.
Educated people in this room are a great way to start.
For the benefit of those who don't know some of the people here, like I have my some friends visiting and stuff, could you all say who you are? Like, do we have a NASA scientist here?
We do, but a few, but I don't think we need to go through the whole room right now. If you want to meet individuals afterwards. Tom's the guest speaker.
Sorry, okay, I just, because he was speaking and I just didn't know who he was, so I just...
Now, this is not my presentation. Walter's Apollo 7. He's been up in space.
Let Tom introduce if he's okay.
Tom does all the really smart demand stuff on it. I'm a physicist, not a environmental scientist.
Right.
And I stick to the facts. And so when I talk to people today, like I occasionally do about this, my appeal is to quit listening what you're being told, to go look at the data yourself and don't buy just what you've been told on that. And I'll give you just one more example. In here, I guarantee you that, I bet we're at 1,000 parts per million CO2 in here.
Oh yeah, let's breathe in again.
You got a lot of hot air for me.
But excuse me. What was going to give you the breakdown? Oh, our atmosphere, and I'm sure some of you people in here, if you're into this kind of science, so you know that, but in our atmosphere here, that's made up of, let's see, 78% of our atmosphere is nitrogen, 21% is oxygen. That leaves 1 more percent. And of that 1 more percent, it's made up of 4 or 5 different gases down there. But one of those is carbon dioxide. And the carbon dioxide goes about 3.4% of that 1%. And of that 3.4% or 3.6%, I don't know exactly what it is right now, is human cause. Part of that is human cause. And I think it's around let's say 3.5% also. So if you take a look at the whole thing, it says human caused carbon dioxide today in our world is equal to 0.001% of the atmosphere.
Right.
I do want to say this though, because I think it's important for the people in the room to know, is that this gentleman here allowed us, paved the way for mankind, for the U.S., should I say, to actually be able to go to the moon in the first place. I think that's important. And most people today don't even know that we actually landed on the moon more than once. I hear this all the time. They say, oh, we had more than Apollo 11. It's unfortunate. Yeah.
It was a Hollywood production.
Maybe they know about 13 because they know the 13 didn't make it, and because of the movies, Hollywood. Otherwise, this is how uneducated our society is, and you do have living history in this room, and what we are fighting to prevent is that the space program does not just be buried and put into some relics of history in the past.
Now we're going to try to
space
boost
program
it.
alive.
We have a great guy now as administrator of the agency, Jim Bridenstine, who I'm very pleased was selected. But there's more people in this room. You got George Stegemite here.
We have a president who actually has wants to
who also
mission.
helped get us into the present, not necessarily the moon, but where we are today. And where we are today is at the golden age of humankind, if you really think about it. Yes, sir.
Yes. Will there be anything done? I know that we're talking about climate change and all, but y'all are talking about the space programs and all that. I know that the U.S. has canceled further, I wouldn't say just cancel it, but like explorations to, I guess, the moon and everything. I heard President Obama, when he was in his terms, he said that we didn't have the technology now to go to the moon. Is that true?
No,
because
it's not true.
And why are we not exploring further?
Look, like I said, we have a new administrator for the agency who has his mental act together. I'm looking for the agency to make. I'm looking for NASA to become great again, not just America to become great again. I'm looking for people who are politicians like Keisha to help support that policy. We can do it. When I see the cancellation of the shuttle, my analogy is the equivalent of owning an island and then sinking the rowboat that gets you there. And what's worse, we have contracted with the Russians to pay them $80 million per astronaut that they send up there. Now, we used to send a shuttle up for about $200 million. We put 10 people on board. That's $20 million per person. Doesn't take a math genius to figure out they were paying 4 times as much. What's worse, we contracted with the Europeans when we had the shuttle to take their people up for $20 million. And now we're paying the Russians $80 million per European that goes up there. Think about that money is going to Russia. It supports their space program. Those jobs that used to be in the Cape are now in the Soviet Union. And I firmly believe that the open mic situation with Obama and Medvedev, that most of you have seen, and if you want, you can Google it, open mic, Obama, Medvedev, was Medvedev saying to Obama, hey, we need help in our space program. We don't have the wherewithal to do it. And Obama answers, wait till I'm re-elected and let me see what I can do. And that's exactly what happened. Once Obama was re-elected, we started sending those millions and millions of dollars to Russia to support their space program and ours, our manned space program. We still train astronauts. We train them to go up in Russian vehicles. That's going to change, guys. It's going to change for the better. I think Bridenstine is a brilliant choice for administrator. He's knowledgeable. He knows astronautics. He knows aeronautics. I really have a lot of confidence in what's going to be our future. Okay? So the fact is our space program has declined. NASA as an agency is markedly different than when I worked there. Markedly different. It has become a little bit of a bureaucracy, no, not a little bit, a lot bit. And I think we can change that. I really believe it will happen. Yes, sir.
Yeah, I actually have kind of two questions, but they both feed into this question of cooperation between the U.S. and Russia and other countries on this. First one is on an actual strategic defense of Earth from things like this undetected asteroid that just buzzed South Africa, and previously you had this actually very damaging one in Chelyabinsk.
Oh, you had an explosion one over Russia.
Then the other question is on the
be in touch.
The question of the detection possibility for things like what Keisha mentioned at the opening, which is seismic events and volcanic events. I know that there's a Russian scientist named Sergei Pulinets who had done some research on actual warning signs, including the ionization of the atmosphere near where these things occur. And it seems like these are areas that we should be researching, and it also seems like they're natural areas for cooperation between us and other countries.
We got to solve real problems.
Yeah.
We do need to do research. We do not need to scare the crap out of little kids by teaching them that they're going to get inundated by sea levels that cannot get there because there isn't any ice water melting. So we have a ways to go. Be active politically. Vote for the right people. Yes, ma'am.
Yeah, I just think that one thing that really inspires me, you know, hearing from these people involved in NASA and so forth, and yourself, you know, that if what we did for the Apollo program had such a massive impact on society, what the development of fusion power is going to have is going to, I mean, you know, it's going to be a real booster.
But by the way, that's what you got to focus on. You have to focus on the things that will really help humanity as opposed to hurt humanity. Preventing people from building a power grid in Africa hurts humanity. Now the Chinese are getting smart.
For the Chinese,
what
right?
the Chinese are doing, they are helping now. They are building railroads and putting in grids. Why do they want to do that?
Raw materials.
Nah. They don't want the raw materials. They want to develop markets for themselves.
Sure.
You can't sell a flat screen TV to a guy living in a hut who earns $2 a week. You know, it just isn't going to happen. But if you develop the whole planet so that the whole planet can trade with each other, learn from each other, do research with it. And by the way, the Chinese have a decent space program. They're landing, they're putting a lander on Farside, which, and we should be working with them. All right, thank you. That's just a personal editorial.
We're personally saying, great.
George, what do you got? Anything? You're thinking of a question, I can tell.
No, this is out of my domain,
No,
this whole subject here.
This is one of the most brilliant guys you'll ever meet, by the way.
Well, I'll
I think you folks can double check me on this, but it is against the law for NASA to work with cooperative with China.
Yes.
So you
Yes.
have got to tell your representatives that you want it legal for NASA to cooperate with
Absolutely.
China.
But for what I understand right now, there's even a move to stop the new National Space Council and NASA from working with China. I don't know how.
We're gonna change that. Right?
Yeah.
And if you got elected, you're gonna change that.
Absolutely.
And we won't have a ride to the moon if we keep that up with Russia too.
Right. Right.
And what I want to do is clone people like Alex over there, like George over here. Like you do. and spread this, our ability to look at technological problems, solve them, and get that all over the world. Big, big help. That's what the future is going to be, folks. Not the scare tactics, not the taxation.
One of the things I say about STEM and STEAM and all these programs is that Einstein had just read the books and answered the multiple choice questions, we wouldn't have the theory of relativity.
Einstein's victory was the 1919 eclipse, when he was able to show that the relativistic bending of light was real. That's what gave Einstein credibility. Then the people say, well, this guy must know something. And of course he did. And yet, the intriguing thing most people don't know about is that Einstein was barred from working on the Manhattan Project by the FBI because he was a German. So here's a guy down, first of all, Einstein was Jewish. Okay? So to think of the motivation that Einstein might have had to help the Manhattan Project along, I think we might have gotten to the atomic bomb a little bit earlier than we did. The fact that we still did it was still pretty good.
The FBI is about as smart and useful today as it was then.
Now again, this is Keisha's program, folks. I'm just a guest here, you know.
I was on the question of cooperation. One thing that people should know is that U.S. cooperation with Russia, in particular, which was brought up, is today is the 30th anniversary of President Reagan's visit to Moscow to visit with President Reagan's visit with Gorbachev, and on that anniversary, the former president of Russia, the Soviet Union, came out and said that the U.S. would greatly benefit at this moment from a meeting, a summit between the two leaders, both President Trump and President Putin.
Gorbachev said that.
Gorbachev, yes. This is important right now because what we're talking, if we don't have this relationship to move forward, and what we're talking about today, the only way we're going to actually solve and address these needed questions is that we don't have to spend all of our time fighting against the witch hunt that is trying to say that the President of the United States colluded with the Russians and should be working with the Russians. And you can't take the politics out of it because it's absolutely political. It's a political fight. Everything we're talking about right now is absolutely political. If, in order to build this, if we were to build this dam, who's going to build it? You're going to have one nation build this? You're going to have many nations involved in this because who's going to be in charge of something like that?
I think the Chinese would like to build it.
Well, yeah, probably would be the only ones that have the capability to do so.
Because China does not want to be under 3 feet of ice, 8 feet of ice, 8 miles of ice. There's some real motivation for them to do it. And I think the Canadians may want to jump in too.
Right. So I'm going to also ask that people, before you leave, this is a very important proposal as to how we can actually address the needed solutions in the United States to get the U.S. to cooperate with nations such as Russia, China, and the economic solutions in the United States so we can make NASA great and our space program great again. This is a platform which I'm fully endorsing by economist Lyndon LaRouche, and also working to say, look, if we have a credit program to invest in our space program, our infrastructure, then we would be able to build the types of infrastructure and the space program that we need right now. But we're being told that we don't have the funding to do so. And I disagree with that, this idea.
So do I.
Yeah. I think we do have the funding to put into our space program. And anybody who says differently is jeopardizing the future of the United States.
Thank you. Now, are we done?
It might be done with you. Thank you.
I'll hang around and try to answer any questions.
This can't ever be done, but we have to quit sometime tonight.
Oh, on the meeting.
Wow.
Yeah, this place is open 24 hours.
Good to see you again.
Right. I hope you enjoyed it.